Well, welcome everybody. So my name's Greg Podgorski. I'm the Associate Dean in the College of Science, but more importantly, I chair the Science Unwrapped committee, and I love Science Unwrapped, and you must too, because you're here. So welcome tonight. And I'm glad to see a lot of young people in the audience. This is a landmark for us in Science Unwrapped because it's the first time in 2 years where we're starting to get back to the good old days of after talk, hands-on science activities. So we're really looking forward to that. And I think it's going to be a whole lot of fun. So I'm glad so many kids are here. And speaking of kind of kids, right? We have a group of Green Canyon high school students. Am I right? Ridgeline, I'm wrong. Okay, wrong in a bad way, okay? I have made mistakes occasionally that I've lived to regret. This is one of them I'll remember. So what's your mascot at Ridgeline? Riverhawks. The Riverhawks. So we have a bunch of Riverhawks flying in.
I don't know what they are.
You're what?
A bunch of different schools.
Different, all right, bunch of different schools. What's any Green Canyon students? Okay, so it wasn't completely wrong. Your mascot. What's your mascot at Green Canyon? Whoa, you better know this. All right, okay. What is it? It's not a bobcat, is it? Is that Skyview? Skyview's bobcats. What's Green Canyon? All right, so stump that. Think about it, and sometime later in the talk, we'll share mascots over here. So welcome Riverhawks, welcome whatever the mascot for Green Canyon happens to be. And I put you on the spot. The Wolves? All right, we'll figure it out. But welcome to Science Unwrapped. So anyway, this is an exciting night for me, and I'm glad we've got a lot of people here. So I really will introduce our speaker, Dr. Katie Potter, in just one moment. And Dr. Potter's talk tonight will be What Goes Up Must Come Down, Cleaning Up the Atmosphere with Geology. Okay. But before I get there, I want to do some thank yous. I always thank USU Media Productions, who makes the live streaming and recording of this event possible. And for those of you who are at home for the live streamed event, please submit your questions to AggieCast. There's a little questions box on AggieCast. But when you do that, wait until you see the notification that the moderator has joined the chat. This way, you make sure your question comes in. I will take those questions as they come in, and we'll take them at the end of the talk. Speaking about volunteers, we have a ton of volunteers that make Science Unwrapped possible. I would like, though, to recognize two of our steady volunteer groups, and those two are let's see, I'm trying to think what HOSA, the acronym, means. And I'm going to cheat over here, so it's Health Occupation Students of America. They have been with us forever, and they're greatly appreciated. Another group, which actually made the attendance of our high school students here possible, is the Society for Women Engineers. And I'd like to recognize both groups by the representatives here tonight. So in alphabetical order, for HOSA, Keith Wilson. Keith, are you in the audience? Excellent. Keith, you come on down. I'm going to make sure I've got this and I have the right one. So while Keith is coming down, again, HOSA, the Health Occupation Students of America, has a table tonight, as they always do. So Keith, we've been instructed. Nicole. Okay. So Keith, standard. So thank you. I'd like to give this to you in recognition of your long-term volunteering activity. So thanks very much. Okay. Okay, thank you, Keith. Thank you very much. And the Society for Women Engineers. And Daniela Rivera is here tonight. You're not Daniela, okay. You could be. So tell me who you are.
Taylor.
Tell me, I recognize you.
I'm Reagan True. Yeah, I used to be my professor.
Ah, okay.
Yeah, for
wonderful.
my classes. But
Okay,
yeah, I'm the
excellent.
president, but
Tell
yeah,
me your
Danielle
name,
is-
please.
I'm Reagan.
Reagan. Hi, Reagan.
Nice to
Okay,
meet you.
so Reagan. For Reagan.
For Danielle.
Okay, for Daniela. Okay,
awesome.
thank you,
I'll be sure
Reagan.
this gets to her.
And
Thank
thanks
you.
for all Society for Women Engineers does. Okay, I'm going to look at the list here, but let me introduce now Katie. So all eyes are on Katie. So I have just gotten to know Katie in the last little more than a week, in that we kind of intersected paths at one of the welcoming events in fall semester for new students coming back. But Katie has a set of interesting stories. Let me share a few with you. Katie grew up in a beautiful corner of Colorado, so the southwest corner in the San Juan Mountains in Durango. And Katie says she has a long-standing interest in geology, and if you grew up in that area, you would understand that. It's fantastically beautiful mountain country. And Katie did a whole bunch of hiking and rock hunting in her early days in Durango. Katie is a graduate of Fort Lewis College, where she got her bachelor's degree. She went on to get a master's at Idaho State University, and then she made an excellent choice and came to USU, where she got her PhD. Okay. Katie is an assistant professor in the geosciences department, and Katie runs a program that I always like to pitch to incoming students, so a geo workforce emphasis within the geosciences, so within the geology major. And geo workforce's emphasis allows students to go through their bachelor's degree and come out with lots of marketable skills for things related to geology, so all sorts of things in the field. So it's a new program that is taking off, and I think it's a really great program. Katie does all kinds of things in the way of research. Her primary site is the Snake River Plain just north of us, but interestingly, Katie gets around, and she just is back by about, 2 weeks or so, I think, 3 weeks? About a month, okay, from a 2-month-long voyage in the South Atlantic off the coast of South Africa, Namibia to be specific, looking at something that you'll talk about tonight, and that is basalt fields that are undersea, and doing a whole bunch of drilling operations off Namibia. And Katie likes USU sort of, but she can't stick around. She'll be going to the Grand Canyon for a kayaking trip starting on Wednesday, and ostensibly to look at some geology, but I think it's to do a lot of paddling, all right?
There's basalts down there.
Yeah, all right, so Katie's busy. She loves to run, to bike, to ski, to paddle, so all kinds of good things. But Katie's going to tell you about geology and carbon sequestration and capture tonight. In her talk, and I'll say it one more time, what goes up must come down, cleaning up the atmosphere with geology. So Katie, thank you.
Thanks for the introduction, Greg. I think this is working. Can you give me a thumbs up if you can hear me? Awesome, great. My name is Katie Potter, and I am a geologist in the Department of Geosciences here at Utah State. And today I'm going to tell you the story of how an often overlooked and underappreciated rock called basalt could hold the key to removing carbon dioxide from the air. And as Greg said, I just got off of a deep sea expedition drilling basalts off the coast of Namibia. Here's the picture. Oh, it's kind of over there. There we go. This is a wild pointer. But I realize many of you might not know what a basalt is. So we're going to begin this talk with a little bit of learning for some of you, and maybe a little bit of a review for those of you who have taken an earth science class or geology. But I'm going to need a few volunteers from the audience to come up here and help me describe some rocks so that the audience, both you folks that are here, but also the people tuning in remotely, can get a sense for what basalt is. So could I have 4 people come up here, step right up, come on down. Oh, just come down. There, perfect, we got 1. So you had your hand up, come on up. One of you, just one of you. Rock, paper, scissors. And then you, right here. Okay, we got our 4. All right, so I'm going to hand you this rock. And come over here. I'll hand you rocks. There you go. Okay, I only have 4, so maybe 2 of you can share. Oh, you can just grab a rock here. I'll give you the hard one. Okay, and there you go. Okay, so what I need you to do is use your hands and use your eyes and come up with a description of your rock that, again, will share the characteristics of the rock with the people in the audience. Who wants to go first? Do you have a question? Okay. You don't want to go first? Oh, I'm going to actually have you go second. This is strategic. I'm going to have you go first. Will you tell me about your rock?
Yeah. Kind of smooth on the top and kind of textury right here. Also has kind of little holes in it. And I know it comes from a volcano.
I see you have a geologist up here. Awesome. Thank you. That was an excellent description. And I'll paraphrase for you. This geologist pointed out that this rock is kind of smooth and it's got some holes in it. And one thing that's interesting about this rock is it's kind of a half of a cylinder, half of a cylinder. And that's because this was drilled out of the ground. This came from the Snake River Plain, just to the north of us. And these holes that you pointed out are actually fossilized gas bubbles. We call them vesicles. Vesicles are just an indication that that lava had a lot of gas in it. Gas is like carbon dioxide. Okay. You're up. Tell me about your rock.
It feels like it's hard. And I think it has hard rocks inside of it.
So it's got hard rocks in it. What color is it?
Like a little grayish.
It's grayish. Awesome. Do you see anything in there, or is it just pretty gray?
There is kind of like white like these.
Okay, so it's got some white marks. That's an excellent observation. You did great. Those white marks are actually where the rock has been broken. Yeah, but this is just a pretty standard lump of massive basalt. It doesn't have any crystals in it. It doesn't have any gas bubbles. And this tells us that the basalt cooled relatively fast on the surface. You did great. Thank you, Big Brother, for helping. And you guys can go back and sit down. All right, how about you?
This is an igneous rock. It definitely came from a volcano. I can see that. It's red. It was from a gassy volcano. I can see that probably a lot of sulfur was there.
Really, sulfur, awesome. That'd be exciting. Great job. You're a geologist too. I don't know that I need to give this talk today. I think everyone knows what's going to happen next. Very good, thank you. All right, so that young geologist pointed out that this is a red rock. It's got a lot of gas bubbles in it. It's pretty light, it's not that heavy. And I'm gonna focus on the red color because that's actually an indication that this, like other basalts, have a lot of iron in it. Iron is a natural ingredient in basalt, and it actually makes basalt typically very heavy. This rock is light because it's got a lot of gas bubbles, those vesicles. So the red comes from oxidized iron. Just like if you leave something metal outside, it rusts. The iron in this basalt has rusted, which is another indication that it cooled on the surface. Okay, last but not least, you had a long time to get nervous up here.
It's this big, it's kind of heavy and it's like brown with spots. It's solid.
Nice work. You are a geologist too. Excellent. Okay. Great job, everyone. Thank you, volunteers, for helping me describe these rocks. That was a great description. So this rock up here is pretty homogeneous looking. It looks like this kind of boring, not boring, no basalt is boring, but pretty uniform looking rock up here, this gray piece of massive basalt. But it's got some white spots in it, and those white spots are actually minerals. This is one particular mineral called plagioclase, which I'll talk about in a little bit. But what this rock shows us is a two-stage cooling history. So we know basalts cool on the surface, but oftentimes they can be made up of mineral ingredients that cool early on in the magma chamber but then get brought up with the lava and cool along with that lava on the surface. So we can see kind of a spotted rock like this right up here. Okay, so you know about basalt now. I'm going to summarize what we learned. It's a volcanic rock. It cools from lava, which is molten rock. It comes in many different flavors. And so we saw some some basalt that's vesicular. It has gas bubbles in it. We saw some basalt that doesn't have any gas bubbles. We saw some basalt that's red. We saw some basalt that has little mineral dots in it. But basalts are all generally compositionally the same. They have the same general ingredients, high amounts of iron and magnesium relative to silicon. Basalts are the most common rock type on Earth. They erupt in every plate tectonic environment. They're all over the place. So odds are that you've probably kicked a basalt down the road, or you've picked up a piece of basalt and thrown it. You've probably seen a basalt at some point in your lives. And now you all have seen basalt, because there it is at the front of the room. So as Greg said, I just got off of a drilling ship. We drilled a lot of basalt. This is me very excited about the basalt. But most of my work actually takes place on the Snake River Plain. And who has driven across the Snake River Plain? Were you really excited and stimulated by the scenery? Some of you were, good. But many of you probably groan when you hear that you have to go to Boise or something. It's a long, kind of flat drive. But it's actually geologically fascinating. And if you drove along the Snake River Plain 8 million years ago, you might have seen something like this. Very exciting. So this is an artist's depiction of a supervolcano eruption, such as what might occur at Yellowstone National Park in the future. But this was taking place on the Snake River Plain over the last 10 million or so million years. And what we see here are very explosive eruptions. These erupt lots of ash, particles of rock, fragments of rock, as well as sulfur dioxide and some carbon dioxide into the atmosphere. And all of that material that gets erupted by the volcano gets circulated around the planet, and it actually reflects back solar radiation into space. So it can cause global temperatures to cool as much as 2 degrees Fahrenheit, which would cause you to want to put on a sweater. That's cold. Other volcanic eruptions that took place on the Snake River Plain and other parts around the world are not explosive. They're gentle eruptions, but they release large amounts of carbon dioxide, not any ash, and not any sulfur dioxide. And these volcanic eruptions are actually responsible for increasing global temperatures. However, foreshadowing, the focus of this talk is going to be that the products of these volcanic eruptions can help us remove carbon dioxide from the air and lower global temperatures. Okay, so I've divided this talk into 3 parts. I don't know why I'm not using this thing. The first part is going to be setting the stage, providing you with a bit of background information about Earth as a system, specifically focusing on Earth's atmosphere and some of the cycles, the carbon cycle in particular, that make things run. I'll talk about why carbon dioxide, too much of it, can be a bad thing, and also why we have an excess of carbon dioxide. And then I'll go into solutions, geoengineering, the combination of geology, engineering, working together, and specifically one type of geoengineering, carbon capture and storage. I'll talk about why flood basalts and their unique chemistry make them ideal candidates for storing carbon dioxide. And I'll talk about where basalt carbon capture and storage is taking place today. I'll wrap up by talking about where we might do carbon capture and storage in basalt, how much CO2 we can store versus how much we need to store, some of the challenges with storing carbon dioxide in basalt, and then some conclusions and final thoughts. All right, so this is Earth. It's a closed system, which means everything that is on our planet, water or any liquids, gases, rocks, have all been recycled over the last 4.6 billion years. And we're looking at this image of space taken from a satellite. And I want to draw your attention to this. And this also is going to highlight another theme of this presentation, which is lots of quiz questions, so you're not going to get off that easily. So I want you to answer this question: what are we looking at here? And pick either A, a very big cloud, B, a big rainbow, a giant rainbow, C, the atmosphere, or D, a very large, very flat alien spaceship. So what is it? Which one of these are we looking at? You can shout it out. Oh, wow. All right, I think I heard some C's. If you said C, you're absolutely right. That is the atmosphere. It is not an alien spaceship. And the atmosphere is very important to us as life forms because it keeps Earth at a stable temperature. It keeps our temperatures at a livable condition. It's not extremely hot and not extremely cold. And our atmosphere is made up of a variety of gases, including nitrogen, nitrogen oxides, carbon dioxide, methane, oxygen, as well as water vapor. The most important, or one of the most important of these atmospheric gases is carbon dioxide, and that's because it has very good, very strong heat trapping capabilities. It also doesn't react with other gases in the atmosphere to form new compounds. And most importantly, it's required for life. We wouldn't have any plants on Earth if we didn't have carbon dioxide. So we need carbon dioxide. Now, carbon is naturally recycled on our planet through the carbon cycle. All of the carbon dioxide that comes out of volcanic eruptions, like supervolcano eruptions, gets stored in vegetation and land and gets stored during the process of weathering. And we also have oxygen cycling of carbon dioxide through a gas exchange. The key with the carbon cycle, the key thing is that all of the carbon dioxide that's naturally released from volcanic eruptions and ocean gas exchange is taken back in, naturally stored by vegetation, land, all these natural carbon sinks. However, when we burn fossil fuels like coal and oil and natural gas and cut down trees, we disrupt the system. We disrupt the carbon cycle. We add more carbon dioxide to the atmosphere than can be stored naturally. And this leads to an excess of carbon dioxide in the atmosphere. So what I told you earlier is significant. Carbon dioxide has this very strong heat trapping characteristic. So when we have a lot of carbon dioxide, more carbon dioxide in the atmosphere are coming from non-natural sources, we have increasing global temperatures. And this connection is known as the greenhouse effect. So what this graph is showing you, on the x-axis is time since 1880, which is about the time when we started taking measurements of global temperatures. This is when thermometers got invented. And what you're seeing on the y-axes are deviations or differences from average temperatures over the 20th century, and atmospheric global concentrations of carbon dioxide measured in parts per million, or ppm. And the general trend is that with increasing carbon dioxide, we see an increasing number of these higher than average temperature years, these bars. So the blue bars indicate lower than average temperatures, and the red bars indicate higher than average temperatures. Now this is a little weird, this center portion of the graph. And we can explain that because Earth's surface temperature resists rapid change. So in the same way that when you push down on the gas pedal in your car doesn't instantly accelerate to 60 miles an hour, Earth doesn't instantly respond to this higher amount of carbon dioxide in the atmosphere. So it takes a while for these temperatures to show up, but they're here. We see them now. Now this is an issue. These warming global temperatures are an issue because they can lead to a domino effect. So increased melting of Arctic sea ice can cause global sea levels to rise. They can also disrupt ocean circulation, especially in the Atlantic. And an increasing amount of CO2 in the atmosphere can also lead to ocean acidification as the ocean absorbs that CO2. And that can throw off food webs, cause the collapse of fisheries, and lead to mass extinctions. And we're already seeing these accelerating changes. So this is a temperature map showing global temperatures. And 2021 was the 6th warmest year on record. Just for reference, Utah's, the general area of Utah is circled there. And this is despite La Nina conditions off the coast of South America, which typically cool parts of North America. We haven't had a cooler than average year in 45 years. And if we continue with our current trajectory, if we continue emitting carbon dioxide at the rate we're going, we will see an increase of at least 3 degrees Fahrenheit by 2100. Unless we remove carbon dioxide from the atmosphere, even adopting renewable technology won't be enough. So we need both. We need to not only switch to zero carbon fuels, but also remove carbon dioxide from the atmosphere to keep global temperatures below 2.7 degrees Fahrenheit. Okay, so I've probably scared you. Now I'm gonna talk about solutions. We're gonna talk about things that are cheerful for a second, and that's geoengineering. So again, this is a combination of geology and engineering. It's defined as I have to read this, the deliberate and large-scale intervention in Earth's climate system. And it can be a variety of scales and complexities. Has anyone ever planted a tree? You have done geoengineering. So you've removed carbon dioxide from the atmosphere by planting that tree. That is a type of geoengineering. It could also be painting your house white. If you didn't know that, when you paint something white, it actually causes an increase of reflection of that solar energy, so you don't need to burn as many fossil fuels to keep your home at a cooler temperature. You could also, as these workers are doing, put sheets over glaciers to prevent melting. Or if you're really crazy and you want to do a really large scale intervention, you'd actually try to put things up in the atmosphere to reflect solar radiation. And we're going to think about that for a while. So this is another quiz question. Why can't we just put a bunch of ash and sulfur dioxide in our atmosphere? And there's a variety of options here. I'll go through them with you. Is it A, we would create acid rain because sulfur dioxide in water creates hydrogen sulfide? Or is it that some areas of Earth would cool while other areas would remain too hot? Or is it that we wouldn't actually be addressing the excess carbon dioxide? Ocean acidification would still occur. Or is it that we could cause increased precipitation and flooding in some areas and drought conditions in others? Or is it E, all of the above? E, awesome, you all got it. Great, yeah, so some of these large-scale geoengineering ideas are quickly abandoned because they would have unintended consequences. They would have potentially negative impacts on ecosystems and populations. So we probably can't do this. But what if it was as simple as sucking carbon dioxide out of the air? We know we need to remove carbon dioxide. How about we just remove it? I'm getting there. That's good. She says she wishes it were that easy, but it is. Yeah, just wait. Okay, carbon dioxide can be removed from the atmosphere through a process of geological carbon capture and storage, which I'm going to abbreviate throughout this presentation as CCS. What this involves is either taking carbon dioxide from the point source, which could be a power plant or an oil refinery, a paper mill, or it could be sucking it out of the air. Then you take that CO2 and you compress it, you liquefy it, you transport it to a suitable site, and you inject it below the surface. And this is happening now. This is not anything revolutionary. CCS facilities are in operation around the world. Most of them are operated by major oil and gas companies as a way to offset that carbon dioxide emission. And then it involves the injection of lithified carbon dioxide into deep sedimentary rock layers or coal reservoirs, coal beds, or areas where these oil and gas companies have extracted oil and gas, and we have empty pore spaces that are ready for that CO2 to be injected. This could also be injected into saline reservoirs, and that just means salty water, too salty to drink or irrigate crops. So a pretty suitable place for carbon dioxide. There are some limitations with this, though. It takes a long time for that carbon dioxide to stabilize and turn into a mineral. And it's also a little bit risky. This carbon dioxide in its liquid form can actually leak out and end up back on the surface, which is not what we want. So I'm going back to this original slide. Remember when I told you that the products of some volcanic eruptions can help us decrease CO2 levels? Yeah, you remember this slide? Well, specifically, these eruptions are flood basalts. And flood basalts are the products of huge volcanic eruptions. They cover wide areas in basalt lava. They can create multiple layers of basalt over time, so layer stacking upon layer, stacking upon layer, each layer the result of an eruption. And they can erupt geologically fast, sometimes on the order of 1,000 years, but up to 2 million years. Here are where flood basalts are located. So every continent has a flood basalt province. Every ocean has a flood basalt province. I was just hanging out here on the Walvis hotspot track, but we have one closer to us, the Columbia River basalts of eastern Oregon and eastern Washington. And again, these are all over the place. And they form as a result of hot material upwelling from the core mantle boundary. And I'll provide a little bit more information about that on the next slide. But I just want to show you here that they're associated with all types of plate tectonic boundaries. If you remember, Earth's crust is separated into individual plates which interact with each other and create things like earthquakes and volcanoes. And so we have some of these flood basalts associated with plate boundaries in Iceland. Iceland's a good example of a divergent boundary where the plates spread apart. We have some of these flood basalts associated with subduction zones off the coast of North America, and that involves one plate sliding below another plate. And we also have flood basalts that are not associated with plate tectonic settings at all, that occur in the middle of plates, like Hawaii and Yellowstone. So as I said, hotspots involve this hot material upwelling from the core mantle boundary. They're extremely hot and they melt the overlying crust. And that crust could be continental crust like it is in Yellowstone, or it could be oceanic crust like it is in Hawaii. But the products are the same. Large amounts of lava, these flood basalt eruptions, which are always associated with hotspot volcanism, this mantle upwelling. And just to point out, the core mantle boundary, the core mantle boundary is just this area between the outer core and the mantle. So these come from pretty deep below the surface. They produce a variety of eruption types. Sometimes they produce shield volcanoes, which are shown in this image here, just like in Hawaii. Sometimes they produce fissure eruptions, like what we see on the island of Iceland currently. And fissures are just big cracks in the ground that lava erupts through. And sometimes, or most of the time, these flows move as pohoihoi flows. And pohoihoi is a native Hawaiian word for paddling, for to paddle, which I guess is indicative of the ropey surface that forms on the top of pohoihoi as it cools. It's almost like you put your paddle in the water and the water is rippling around it. So the name describes the shape of the basalt as it cools. All right, so I did this cartoon. It's very poorly drawn, but you can see kind of how these inflated pohoihoi flows move. It's kind of like an inchworm. And as they erupt, the top and the bottom of the pohoihoi lava flow cools. And then as you get enough thermal material, mass, some lava coming in, it actually advances that pohoihoi lava flow. They kind of, again, move like an inchworm. New pulses of lava fill that interior. It's almost like a tube of lava moving along. But again, that top and bottom surface solidify while the rest of the lava is still molten on the interior, and they kind of move along. And I don't know that this cartoon does a good job of explaining this, so I'm gonna need your help. I need you all to stand up, because we're gonna dance. Okay, so I got some music to get us in the mood for our pohoihoi dance, our inflated pohoihoi dance. And what I want you to do is pretend you're coming out of the vent, erupting on the surface, flowing, and then you kind of stall out as you crystallize. You gotta freeze a little bit. But more lava is coming behind you, so you're inflating. And then so much pressure builds up that you squeeze out the front, and we keep going. It's hard to do with one hand, but you guys get the idea. And this is great because it allows Pohoihoi flows to move up to 40 miles away from the vent. So this is very efficient. It doesn't look efficient when you guys are doing it, but it does work, I promise. All right, thank you. You all are excellent dancers. You're pros at the inflated Pohoihoi dance. Oh, we don't want to start that over. Okay. All right. So, you did great. Thank you. I think we should go on tour, the inflated Pohoihoi dancers. What happens over thousands of years when you have these inflated Pohoihoi flows erupting? They stack on top of each other, and they can create these thousands of feet thick packages of basalt. And this is what characterizes flood basalts, are these thick packages of lava. Some of these flood basalts have a bad reputation because they put so much CO2 in the atmosphere that they can really disrupt ecosystems. And one of these examples is the Deccan Traps of India, which erupted 65 million years ago. And this eruption covered about 2 Utahs with basalt, so a lot of basalt. And many of you have heard about the 65 million year old time frame. This is the end of the Cretaceous period. And there's some creatures, famous creatures that went extinct about this time. So what creatures went extinct 65 million years ago? Is it A, fish, B, dinosaurs, C, unicorns, or D, trilobites? Not just one. You can only pick one. If you picked B, you are absolutely right. The dinosaurs went extinct. Very sad. And it's probably not the case that the eruption of the Deccan Traps caused the dinosaurs to go extinct. That was the Chicxulub impact off the coast or in the Gulf of Mexico. But this eruption probably contributed to the extinction. It probably weakened the dinosaurs and added to, their bad times, their sad times. All right, here's a little bit clearer example of an extinction event caused by a flood basalt. This is a picture of the Siberian traps in Russia. And the eruption of these basalts occurred 51 million years ago and closed out the Permian period. This was a huge eruption. This covered 18 Utahs with basalt. And it probably caused the extinction of 70% of land vertebrates, that's everything with a backbone, and up to 81% of marine creatures. And again, this excess CO2 definitely contributed to these creatures going extinct. But I have to say, I'm kind of glad this thing doesn't live anymore. That's terrifying. Okay, so other flood basalt provinces aren't responsible for extinction. Yay. This is the flood basalts in our neighborhood. Here's Logan for context. So we see the Columbia River basalts of eastern Washington and Oregon, and then the Snake River Plain of southern Idaho. These erupted between 16 million years ago in the case of the Columbia River basalts, and as early as 2,000 years ago in the case of the Snake River Plain. And that eruption occurred at craters of the moon over here. And no extinctions, as I said. These basalts are actually indirectly related to magnificent potato growing conditions because the Snake River Plain is an excellent reservoir for water. And I'll talk about why that is in the next slide. Okay, so here's some basalt flows. And as you guys saw when you did the inflated Pohoihoi dance, the tops and bottoms of the flow crystallize first, and those become really rubbly as that flow is advancing, as it's flowing down gradient. And so you'll see those flow boundaries, the tops and the bottoms, very rubbly, very crumbly. But the interior of the flow is massive and impermeable, meaning no fluids can pass through it. So in the Snake River Plain, that aquifer is stored in this part, in the flow boundaries. Those boundaries boundaries between subsequent flows or new flows. If we drill into the Snake River Plain and get some core like this, drill core, we can see examples of flow boundaries. So here's that rubbly stuff, that's a flow boundary. And in these massive areas, where we don't see a lot of rubble, where it's kind of have some vesicles, those are those interiors, those flow interiors that are impermeable, that can't let any liquids or gases or anything pass through. They're solid, they're caps. So why is basalt storing, or basalt great at storing CO2? Well, another component that makes basalt so great is they contain mineral ingredients that naturally react with carbon dioxide to form new stable minerals. And this is a very, very tiny slice of basalt that is a picture of looking down a very special microscope, a petrographic microscope. And you can see those mineral ingredients in the basalt show up in this image. And I'm going to go through them one by one to talk about why they're so great at storing carbon dioxide. Plagioclase is the biggest mineral ingredient in basalt. It makes up about 31%, and it's, oops, I'll go back a little bit. So here's plagioclase. It's kind of this blocky black and white stripe, sort of like a zebra mineral. There it is in hand sample, so a piece of mineral that you could pick up and hold in your hands. And the mineral ingredients are calcium, aluminum, and silicon, or silica. And when we add carbon dioxide in water, we can form new minerals like calcite and dolomite. And here's the next question. Where is carbon dioxide stored in these minerals? Here's the chemical formulas. Where does that carbon dioxide show up? Is it A, right there? Or is it B, right there? Yeah, B, nice. So this grouping, carbon and oxygen, is actually what we call a carbonate. Well, in the case of CO3, it's a carbonate. And carbonates are very common minerals. Calcite and dolomite are examples of carbonates. And we call anything a carbonate that has this grouping of elements. So let's go to the next basalt mineral. This is pyroxene. You can see pyroxene as this kind of greenish, rounded mineral on the left side of this thin section photomicrograph. And here's a bigger piece of pyroxene. This is something you could pick up and hold in your hand. Now, pyroxene has a whole sort of laundry list of element ingredients. It's got calcium and sodium and magnesium and iron and aluminum and titanium, as well as some silica. And then we add carbon dioxide and water to it, we can create minerals like calcite, dolomite, and magnesite, all of which have that lovely carbonate that's great for storing carbon dioxide. The final mineral ingredient is olivine. It makes up about 9% of basalt. It's visible as this beautiful blue mineral in the upper left-hand corner. This is what basalt really looks like if you picked up a piece of it. Anyone with a August birthday in here? Nice. So olivine, the gem variety of olivine, is called peridot, which is your birthstone if you are an August baby. And olivine is pretty simple to make. You just add some iron and magnesium and some silica. And you can break those down when you add carbon dioxide and water and create new minerals like magnesite and siderite, which is an iron carbonate, and anchorite, which has a lot of mineral ingredient or a lot of elements, as well as that all-important carbonate at the end. Okay, so let's talk about how we can store carbon dioxide below the surface. The first thing we need to do is find a good location. And this is going to involve some science. So we need geologists to find a place that doesn't have a lot of active faults or faults in general, because does anyone know what can happen if we inject fluids and there's a fault nearby? Yeah, it can actually cause that fault to slip, to rupture, and we call that induced seismicity. It's actually kind of an accidental earthquake. So we don't want to do that. We need to know where all the faults are. We also want to avoid aquifers or groundwater, because we can also cause that water to become acidic by injecting carbon dioxide in it. So that's the second step. Another thing we need to do is do kind of a site characterization. We need to drill basalt in that area and figure out exactly where these flow boundaries are located so we know exactly where to inject the CO2 so it won't escape, so it can form these carbonate minerals. And we need to know the composition and the mineral ingredients in that basalt so we know about how much carbon dioxide can react with those minerals to form our stable carbonates. Then we need to capture the carbon dioxide from a point source, like a power plant, or we can suck that carbon dioxide directly from the air. It's true, we can do it. And then we need to pressurize it and dissolve it in water. And you've probably, if you've used a soda stream, you have done this. This is a relatively easy process. You have drunk carbonated water if you've drink pop. The next step is to inject the carbonated water below the surface, and we need to do this between 3,000 to 13,000 feet below the surface. And you see some old mains popping up because I'm showing you the equivalent depth that we need to inject this carbon dioxide. It's about 54, or at least 54 old mains deep. Old main tower is about 60 feet tall, so we need to go at least that depth, and up to 215 old main towers or old mains deep. So this is pretty deep. And we'll just keep going, we'll let it go. And the reason for this is we don't want that carbon dioxide to leak out. We want it to stay in place, so it's kind of pressurized below these basalts, below these massive flow interiors so that it does its job and forms carbonate minerals. The next thing to do is monitor that site so you can tell if the CO2 is doing what it's supposed to do or whether it's sneaking away, whether it's leaking out. And then you repeat. You do this over and over again. And what happens is that the basalt will keep that CO2 in place. The fractures, the rubble that is associated with these flow boundaries will act as a surface for reactions to take place. And then we'll have the formation of these stable carbonate minerals: magnesite, calcite, dolomite, inkerite, and siderite. There they are right there. So this is actually a basalt that was drilled from one of these sites, these carbon capture and storage sites. And so you can see the results. We have carbonates. We have liftoff. Okay, so this has happened. This happened at the Wallua Basalt project. This was a pilot project to test the feasibility of whether we can inject carbon dioxide into Columbia River basalts. This is eastern Washington, outside of Pasco. In this case, the point source is a paper mill nearby. And between July 17th and August 11th, 977 tons of carbon dioxide were injected at the site to depths between 2,720 and 2,785 feet. And that CO2 is still there. It's still, go this way. It's still there. So it hasn't escaped. It's forming carbonate minerals as we speak, which is great. So how does this work? Point source capture? Well, we need some engineers to help us with this. But we take a pipeline from the smokestack of your point source, whether that's an oil refinery or a coal-fired power plant, and we can actually separate the gases into components. We can pull out all the carbon dioxide and store it separately and allow those other gases to migrate back into the atmosphere. This is also happening on a larger scale in Iceland. So this is the Hellisheidi plant. This is associated with a geothermal power plant because there's lots of heat in Iceland. And the CO2 point source in this case is nothing. So this is where we're actively taking carbon dioxide out of the air. During the test phase a few years ago, 90% of the injected carbon dioxide turned into carbonate minerals within 2 years. So this did work. And currently this is in operation. It's capturing about 4,000 tons of CO2 per year, storing it below the surface as carbonate minerals. So how does this work? Direct capture. Well, we take ambient air, which is the air all around us, and you pass it through a filter, and the CO2 sticks to the filter. When we collect enough CO2, you can actually heat up the filter, and that releases the CO2. And the cool thing about the Hellisheidi plant is it uses geothermal heat to heat that filter and release the carbon dioxide. That carbon dioxide is concentrated, and then when we collect enough of it, we can inject it below the surface into the beautiful basalts that make up the island of Iceland. Okay, so now I am at the final part of the talk, and I'm gonna talk you through some of the logistics. So, and a final quiz. This is to make sure you've all been paying attention. Where can we inject carbon dioxide? Any of the red spots. I heard one of you say it. That's right. So each of these red things on the map is a flood basalt province, and we can inject carbon dioxide anywhere. I was just on a deep sea ocean drilling boat, so I know this can happen. We can drill in these locations, and we can store CO2. It's already happening in the Columbia River basalts up here, and it's also happening in Iceland. So we have many different options for these carbon capture and storage locations in the future. And the other cool thing about this is we don't have to just do it in one spot in one of these flood basalt provinces. We can drill here, we can inject carbon dioxide here, we can inject carbon dioxide here, we can inject it here, and here, and here. So we can get every single flow boundary and inject carbon dioxide and know that it will be forming beautiful carbonate minerals that are stable and aren't going anywhere. Okay, so basalt has a huge amount of storage potential. We can inject and store 5,000 billion tons of carbon dioxide, which is all of the carbon dioxide produced from fossil fuel burning, the burning of coal and oil and natural gas. But global emissions are currently 35 billion tons a year, which is about 5 billion fully grown elephants that we're pushing into the atmosphere. And currently, technology only allows us to store about 25 million tons of carbon dioxide per year. So the carbon capture and storage technology that we have will only let us store a tiny amount of these currently high global emissions. And we know that in order to allow these ecosystems on planet Earth to stabilize, for our natural growing conditions, to allow as many species to survive, we need to stabilize carbon dioxide levels at about 350 parts per million. And just for context, they're currently at 418. Scientists say that we need to remove between 100 and 200 billion tons of CO2 to keep global temperature increases below 3 degrees Fahrenheit. So we got some work to do. And that brings me to the sea carbon capture and storage elephant in the room. We have location considerations. So we need to find locations that are away from faults, away from groundwater, to avoid induced seismicity, accidental earthquakes, and groundwater acidification. Oh, I skipped one. The location. We need lots of basalt. We need to have thick packages of basalt with beautiful flow boundaries where we can inject this carbon dioxide. But that's not really a big problem. We have lots of these all over the place. We can find suitable locations. There are risks, though, as I just pointed out, earthquakes, induced seismicity, and groundwater. There's also really high costs involved with this project, with carbon capture and storage in basalt. You need about $400 to $500 million to build one of these carbon capture facilities. And it costs about $60 per ton of carbon dioxide. And to put that into perspective, we need to remove 100 billion tons of CO2. So this is very expensive. There's an energy cost. So we need to use energy to pull carbon dioxide out of the air and drill or inject it into the subsurface. Luckily, this can be overcome in places like Iceland that have renewable energy like geothermal. We can use that non-carbon emitting fuel to inject CO2 and extract it from the atmosphere. The biggest problem is scale. Is it possible to remove carbon dioxide fast enough to prevent climate effects? We have a lot of CO2 to remove, and we know our technology isn't really currently up to the task of doing this. So in conclusion, we have some issues with basalt carbon capture and storage. And we know that there's too much carbon dioxide in the atmosphere. We also know that carbon dioxide emissions continue to be too high, And we need to rapidly scale up our technology to allow ourselves to remove as much carbon dioxide as possible. However, there is something we can do. You can do. You can try to reduce your carbon dioxide emissions. And you can advocate for switching to low or no carbon dioxide emitting energy sources. And you can lobby your legislators to put money into research and development for this technology, other climate mitigation technology. And you can become a geologist, because we need more geologists to help study these problems and find ways to solve our problems. So become a geologist, but also recognize that carbon dioxide capture and storage in basalt is going to be very helpful at removing carbon dioxide from the atmosphere, but it's not the only fix. It's not our silver bullet. We also need to reduce our consumption to avoid the worst effects of global climate change. So with that, I'll take your questions. Thanks so much for being great dancers and good listeners, and fire away. All right, I see you back there. What's your question? That's a great question. So the question from the crowd was whether that 35 billion tons of CO2 is man-made or whether that's including natural emissions. That is man-made emissions. The total. Oh, that's a great question. I don't know that number off the top of my head, but if you send me an email, I can send that your way. Okay, how about over there? Can you make carbon dioxide? Carbon dioxide can kind of be recycled through you when you burp. After you drink soda, that's releasing the carbon dioxide that was stored as a fluid in the pop. So you're like a conduit for carbon dioxide. Yeah, you are contributing to carbon dioxide. Okay, next question. How long will this take? Is that your question? Great question. So the audience member asked how long this takes. Are you asking how long minerals take to crystallize, or? Ooh, how long before we have too much CO2 in the atmosphere? Oh, until it's clean. Oh man, well if we ramped up, if we hit every basalt province, every flood basalt with carbon dioxide, I don't know, someone can do this math problem. 4,000 tons a year, how many plants can we build? I don't know, I would say a while. That's my scientific answer. It will take a while to clean up the atmosphere. Okay, any other questions? Way back there. Oh, that's a great question. Okay, so your question is, it's eventually going to come back out even if we store it in minerals. Is that right? Okay. It's actually not going to come back out on human timescales. It's actually, the only thing we really have to worry about for this is plate tectonics, because that is the way to release it via volcanism. If that plate that contains those carbonate minerals subducts and melts, that's going to release the carbon dioxide, and then it will come out in a volcano. So it's stable for millions and millions and millions of years, at least enough time for us to, whatever happens to us. So we're safe. Great question. Okay, any other questions? Yeah. That's a great question. So the question from the audience was, what makes this process so expensive? Is it the drilling? Is it the active removal of the carbon dioxide? I'm paraphrasing for you. From the point source, is it sucking the CO2 from ambient air? It's a little bit of everything. It's millions of dollars to drill. It's also expensive to even pick a site for this because you have to do that site characterization. You have to know what's going on geologically. And then, of course, building those facilities is very expensive and keeping them operational. The other limitation is this is not profitable. No one's making money by pulling carbon dioxide out of the atmosphere. So that's a big limitation. There's no incentive to do this, really, aside from, saving our climate. All right, you have a question, the geologist in the room.
What will happen if we suck 60 tons of carbon dioxide out of the atmosphere every second? How much carbon dioxide would we carry out in a year?
Oh man, you're asking me a math question? We need to ask these engineering ladies what the answer is. Okay, your question. A lethal level. Ooh, good question. I'm not sure. I'm not even sure what a lethal level is. I think probably the plants would be happy for a long time before. And actually, there's that exchange of plants, giving off oxygen. So I guess as long as we had a lot of plants, we might be all right. But I actually don't know. I think we'd run into problems with the high global temperatures before we ran into problems with lethal concentrations of CO2. Humans can't survive at high temperatures, so that's our problem. Yeah, over there. Ooh, great question. Are there any other minerals that are suitable for storing CO2? Yeah, any carbonate mineral, and there's a bunch of them. So these are kind of the easiest ones to form, the ones that I showed on the screen, like calcite is really common. You can go up Logan Canyon and find calcite. It's all over the place. So there are other ones, but these are the easiest to form. That's a great question. Yeah. Moki marbles. I thought those were iron nodules. I could be wrong, though. Are you Googling? I can't beat Google. Okay, so iron oxide and sandstone, you still need that carbonate because that's what's going to trap the CO2. Great question, though. Moki marbles are neat. It'd be great if they had another use. Okay, yeah. Yes, carbon credits. So the question from the crowd, good question, is have there been any companies that have invested in this? I'm paraphrasing, because of carbon credits. That is one of the reasons why the major oil and gas companies are doing carbon capture and storage in those oil and gas reservoirs. But as far as incentives for injecting it into basalt, not as much. And that might change as increased awareness, increased push toward divesting from fossil fuels and investing in renewables. This could be a big part of that mix. Great question. Okay, any other questions?
Got time for one more if there's another question. Okay.
Yeah.
Good question.
What's the best thing we can do to encourage our kids to have an interest in geology?
Oh, go take them rock hunting. Yeah, I think, well, for me, I'm speaking from my history is rock hunting is good. I don't know. Give them a pet rock. Yeah, and you're doing a great job by bringing them to events like this, because this is a good way to see science in action. So thank you all so much. I've had a great time.
Okay.